So very good evening to all respected members. I warmly welcome you to this guest lecture on basic fundamentals of thermodynamics and AI technologies. So in this today's lecture, we are going to discuss about how AI can be integrated with conventional thermodynamics in core mechanical engineering. Since thermodynamics forms the basic foundation of energy science and engineering, while artificial intelligence is transforming how we analyze, predict, and optimize the thermal systems. So, in this today's segment, we will explore how classical thermodynamics principles are merging with modern AI technologies to create smarter, more efficient, and sustainable engineering solutions. Let us move over to the session overview. Today's session is structured into 6 major subsections. First, we will begin with an introduction to thermodynamics and its significant importance in engineering sciences. Next, we will discuss the 4 laws of thermodynamics, followed by important concepts such as entropy, enthalpy, and Gibbs free energy. We will then examine the traditional engineering applications along with AI integration in thermodynamic analysis, then reviewing of real-world case studies, and finally discuss the future trends and research opportunities. Now let us straight away move over to the basic introduction to fundamentals of thermodynamics. So thermodynamics is the basic science of energy transformation. It studies the relationship among heat, work, temperature, and energy. The discipline is originated in the 19th century through the pioneering work of Sadi Carnot on heat engines. Today, thermodynamics plays a vital role in mechanical engineering, even chemical processing, aerospace systems, environmental technologies, even power generation and biomedical applications. Virtually every system that produces, transfers, or consumes energy is being governed by thermodynamic principles. Understanding this principle is essential for designing efficient and sustainable engineering systems. Now let us discuss the basic laws of thermodynamics. There are 4 laws of thermodynamics establish the fundamental rules governing energy interactions. First one is zeroth law. The zeroth law introduces the concept of thermal equilibrium and forms the basis of temperature measurement. The first law states that energy cannot be created nor be destroyed. It can only be transferred or transformed. This is known as the law of conservation energy. The second law introduces entropy and explains the direction of natural processes. It tells us that heat naturally flows from hotter bodies to colder ones and that no energy conversion process is perfectly efficient. The third law states that as temperature approaches absolute zero, entropy approaches a minimum value. This law provides a foundation for low temperature physics and cryogenic engineering. So these are some of the laws of thermodynamics that are already existing in the past. Let us undergo some of the key thermodynamic concepts. Several thermodynamics properties are very important for doing engineering analysis of thermal systems. First one is entropy measures the degree of disorder within a system and determines the direction of spontaneous process. Enthalpy represents the total heat content of the system and is widely used in energy balance calculations. Gibbs free energy helps to predict whether a chemical reaction or a physical process will occur spontaneously. Carnot efficiency defines the theoretical maximum efficiency of a heat engine operating between two temperatures. Clapeyron equation describes the phase change behavior, while Helmholtz free energy is important in statistical thermodynamics and advanced material studies. Together, these concepts provide engineers with powerful tools for analyzing energy systems. Let us see some of the classical engineering applications in basic fundamentals of thermodynamics. Thermodynamics has numerous applications across engineering disciplines. Heat engines such as petrol engines, diesel engines, and steam turbines heavily rely on thermodynamic cycles to convert heat into useful work. Refrigeration and HVAC systems use vapor compression cycles to transfer heat and maintain comfortable indoor environments. Power generation systems, including thermal, gas turbine, combined cycle, and nuclear power plant, depend heavily on thermodynamic principles. In fact, a significant portion of global energy conversion process is governed by thermodynamic laws, making the subject more indispensable for modern industry. Now let us move on to the main theme of today's presentation, AI-powered thermodynamics. Artificial intelligence is opening exciting new possibilities in thermodynamics. Neural network can predict thermal behavior and system performance with remarkable accuracy. Machine learning algorithms improve process control and operational efficiency. Physics-informed neural network combine basic physics laws with data-driven learning to solve complex thermal problems. Deep learning accelerates fluid flow simulations, while reinforcement learning enables intelligent thermal control systems. Generative AI is even assisting researchers in discovering advanced materials with improved thermal and energy characteristics. AI techniques in thermodynamic systems. Use of AI techniques in thermodynamic systems. Let us look at specific AI techniques used in thermodynamic applications. Machine learning models predict thermodynamic properties such as heat capacity, viscosity, and thermal conductivity. Deep neural networks act as surrogate models for computational fluid dynamic simulations, reducing computational time from days to minutes. Physics-informed neural network incorporate governing equations directly into the training process, ensuring physically meaningful predictions. Reinforcement learning continuously learns from system feedback and optimizes operations in HVAC systems, gas turbines, data centers, and power plants. These technologies significantly improve accuracy, speed, and decision-making capabilities. Now let us discuss some real-world case studies. Several successful applications demonstrate the value of AI in thermodynamics. Google's DeepMind developed a reinforcement learning systems for data center cooling. This system reduced cooling energy consumption by approximately 40%. In gas turbine combustion system, neural network predict flame behavior and combustion efficiency in real time, helping reduce harmful emissions. Physics-informed neural networks have also been applied to heat exchanger design, enabling accurate thermal predictions and predictive maintenance. These examples illustrate how AI is transforming industrial thermal systems through optimization, cost reduction, and improved sustainability. Let us now discuss the integration of thermodynamics, artificial intelligence, and sustainability concepts. Integration of thermodynamics and AI plays a crucial role in achieving sustainability goals. AI enhances renewable energy systems by optimizing solar, thermal, wind, and geothermal energy utilization. In carbon capture and storage technologies, as well as machine learning, identifies efficient materials, and operating conditions. AI-driven thermodynamic models support the hydrogen economy by improving storage systems, fuel cells, and electrolyzers. Smart buildings use reinforcement learning to optimize HVAC operations and minimize energy wastage. These advantages mainly contribute directly on several Union nations' sustainable development goals related to energy, innovation, sustainable cities, responsible consumption, and climate action. Future trends and research frontiers. The future of thermodynamics is closely linked with intelligent technologies. Currently, AI assisted simulations are replacing computationally expensive analysis while maintaining high accuracy. By the late 2020s, digital twins of power plant, engines, and industrial systems are expected to become widespread, enabling real time monitoring and optimization. Looking ahead to 2030 and beyond, the convergence of quantum computing, quantum thermodynamics, and AI may unlock energy efficiencies. Autonomous energy systems capable of self monitoring, self correcting, and self optimizing operations are likely to become a reality, transforming the future of engineering. Before I close the session, I would like to reinforce the following key takeaways of today's program on key fundamentals of thermodynamics application using AI interface. So let us summarize the following key messages from today's session. Thermodynamics forms the basic foundation of all energy conversion and transfer processes. The four laws provide a universal framework for understanding the physical and chemical systems in thermodynamic principles. Artificial intelligence enhances the thermodynamic analysis, design, optimization, and control. Technologies such as machine learning, deep learning, physics informed neural network, and reinforcement learning are enabling real time intelligent engineering solutions. The convergence of AI and thermodynamics will play a pivotal role in achieving sustainability and advancing the future energy systems. So, with this information, once again, I thank you for your attention and participation. I appreciate your time and I wish you a great success in your academic and professional endeavors. Thank you all.